So in this video, we're going to first of all introduce the inverse Laplace transform. So the inverse Laplace transform, as you can see here, looks like this. F of t is L, the usual Laplace transform symbol, inverse of the function f of s. So obviously, we've what the inverse Laplace transforms operation basically is to convert go back from the s domain back to the time domain. That's basically the point of the inverse transform. Now let's look at how we actually do this. Is as you see the table on the right, this is a table of Laplace transforms. So for instance, if we had the function here, so for instance, if we had a function f of s equals, for the sake of argument, 1 over s squared, then we would go over here to our Laplace transform table on this side, the fs side, okay, this side, and we go down and we start noticing, here's 1 over s squared, and what is its inverse Laplace transform? T. So this implies that f of t is equal to L inverse of 1 over s squared is equal to t. So that's it's as simple as that. So another example, for instance, you might have is, for instance, if we had f of s equals 2 over s squared plus 4, okay, or say 4 over, let's say 4 over s squared plus 4. So to find the inverse Laplace transform of 4 over s squared plus 4, then we would go again to our, we will see that, we notice that this is the closest one, okay? However, it has an extra 2 here, so we would do the following. We would leave a 2 outside, and then we would take the inverse Laplace transform, which is sine of 2t, and that would be the inverse Laplace transform of this. So this is basically how the inverse Laplace transform works. It's as simple as that. Just go to the table, find what this matches, and then just work out the result. Now, so here are just some more examples for you to see, just for your reference. You can have a look at them. Okay, let's look at this example. X of s is equal to 2s minus 3 or s squared minus s minus 6. Now, obviously, if we look at our table, we don't seem to see anything that looks like this. However, we know that we can simplify, perhaps factor the denominator. So let's do that and see what happens. So here we can see there the denominator s minus 3s plus 2. Still, nothing here seems to match it. However, we do know that it is possible if we had just s minus a, for instance, this s minus 3 and s plus 2 were separate fractions. This over here, we might have a possibility in this one that you see. So in order to do that, we know there is a way to do this. So by just saying, okay, a over s minus 3 plus b over s plus 2, we can go away and find the partial fractions basically of this. So I'll remind you, this is something important you need to brush up on if it's not that good or you forget it right now. And you can look at my videos on Calculus 2. You'll find videos on partial fractions. Okay, so now the idea would be, if we work this out at the end, the partial fractions would be, so it's equal to this. All right, now if you look at this 1 over s minus a seems to be very plausible. So what we can do is now, this is our xs, of course. So now we can go and find the Laplace inverse transform of xs. So it's equal to, so now we need to be careful. Here you will see that the 3 over 5, we will leave it as a constant multiple. Now this is s minus 3, that's s minus a, 1 over s minus a. So this will just be e to the 3t, okay, plus leave the 7 over 5 on the side, and it's going to be e to the minus 2t this time, because this is plus here. Over here you've got, this is the one we're looking at, s minus a, so we get this result. So you can see that we have now taken the inverse Laplace transform, and we've got our result. So we're back to the t domain. So you can see that this technique is important. You will need it when we go to the next video and look at solving differential equations using Laplace transforms. So that's it for the inverse Laplace transform. We'll stop here. Thank you so much.